Okay, we're looking at Riemann sums, definite integrals, and interpreting area. So what we want to do here is understand the connection between these area approximations that we did in the last lesson and get us closer to doing actual integrals by making the connection between those approximations and definite integrals. And we'll also talk a little bit about the end about interpreting areas under the graphs of functions. So this is sort of the definition of what is called a Riemann sum right out of the learning guide. And what we were doing in the last lesson is actually an example of a Riemann sum, but this is sort of the mathematical definition here. So let our function be defined on some interval a to b. Now a to b is the interval over which we are finding our area. So we have like some starting point a down here, some ending point down here. A was the start of our rectangles, and B was like the end of our rectangles down here. And x, I, b points on AB such that x naught equals A, xn equals B, and then we have these in order x1, x2, x3. So these points, basically these x values, are sort of dividing our function, the function into intervals on our domain. So these sort of boundaries between our individual rectangles, we can call them x1, x2, x3, and in this case, x4. Okay. Delta x be the length of the ith interval. So we talked about how you get that value delta x. We said that this interval, or the width of each one of our little rectangles here, was delta x, and we've made all of our rectangles have the same width. And c be any point in that interval. So by saying c here is any point in that interval, this kind of means you can take that value c to be, we took it to be the left end point in some cases. Other cases we took c to be the right end point. Other cases we took it to be the midpoint. Okay. But we could calculate the area equally well whether we chose any one of those 3 points. And the key that the thing that those 3 points have in common is that they are all located sort of inside one of these rectangles. Left-hand edge of the rectangle, the right-hand edge of the rectangle, and so on and so on. They're located inside these intervals that we've divided our function, our x-axis into. Okay, so the Riemann sum is, again, this thing that we were using to calculate our area. Right, we're taking the sum of over all of our intervals, so from 1 to n in this case. So in this case, n is equal to 5. So we had 1, 2, 3, 4, 5 rectangles. And we got the height of each one of these rectangles by doing the value of that function at the left endpoint, the right endpoint, or the midpoint, multiplied by the width of each one of these. Okay, so all of this is just sort of a general way of specifying our area. Our area is we can say it's, you know, area 1 plus area 2 plus area 3 plus area 4 plus area 5. Each one of these little individual areas was, let's say, each one of the individual ones was the height of the rectangle times the width of the rectangle. The height was given by the value of that function somewhere in that interval. The width was given by delta x. So adding all of this stuff up gives us that our area is equal to the sum, I goes from 1 to n, of this f at c times delta x. So this special definition here, this Riemann sum, is really just the way that we were using in the last lesson of estimating the area under curves. Now, let us take an example of this kind of thing and see if we can make it a little bit better. So here I have that same function partitioned into 2 separate Riemann sums. On the left, I have one for n equals 5. Okay, so the area is I should say, is approximately the sum from 1 to 5 of f at ci delta x. And on the right, I have it partitioned into 10 intervals, so n is equal to 10. Now, which one of these two is a better approximation to the true area under the curve. And we talked about this last time about whether something was an underestimate or an overestimate. So, and we were looking always at this area that is either under the curve, that is under the curve but not in one of our rectangles, or this part of a rectangle which isn't under the curve, which was kind of this wasted space. So I don't think it's too much of a stretch to say that you can tell just by looking at this that the n equals 10 Riemann sum is a better approximation to the curve. It's a better approximation of the true area under the curve because there's less of that red area that is either wasted or included. Okay. The other difference between them is, of course, the width of each interval. As we increase the number of intervals, and if we're keeping A and B the same, our value of delta x gets smaller because we're partitioning this distance from A to B into smaller and smaller intervals. Okay? So we can sort of say that as n increases, this delta x decreases, and area approximation is better. So if we want to make our area approximations better and better and better, we make more and more of these subintervals, and by increasing the value of n. So if we want to make it really, really, really good, what we could do is take our Riemann sum approximation here, the sum as I goes from 1 to n of f at ci delta x, and take the limit as n goes to infinity. Basically, see what happens as we make n infinitely large. So we'll make n larger and larger and larger, and look for sort of a trend in our area estimates. Okay. This, and if we were to take the limit as n goes to infinity, this would no longer be an area approximation. If n gets up to infinity, we would actually be measuring the true area under the curve. So we can actually say that this is the exact area, no longer an approximation. Okay. So this is what we're really after in order to find the areas under curves. Okay. Is this limit as n goes to infinity of this Riemann sum approximation. So we are going to be using this a whole bunch, and we're going to use it so often that we give it a special name and we give it some special mathematical formulation. We call this a definite integral. So we say that this thing, which is called the integral from a to b of our function f at x dx, is actually equal to the limit as n goes to infinity of this summation that we're using to approximate it. So the sum from I goes 1 to n of f at, and I'm going to use I in here, f at x I delta x, where delta x, of course, is given by b minus a over n. Okay, so so this terminology on the right-hand side is kind of awkward to work with, so we're going to use this sort of formalism over here that we have on the left side. So just remember that a here is the start of the area that we want to find the area of. B over here is the ending point for where we're trying to find our area. And this thing in here called dx is what is called a differential. And it's like, it's kind of like delta x, but we're making delta x infinitely small. So delta x was the width of one of these intervals. It's delta x made infinitely small. And I'm going to put infinitely in quotation marks here because if it was actually infinitely small, you couldn't add up a whole bunch of them together and get a finite area. So this is one of these gray areas in calculus where the size of delta x, dx, sorry, is as small as you need it to be to answer the question. It's a little bit odd. All right. So when we see now, sort of with this in mind, we'll now take a question that looks something like this. Use a midpoint Riemann sum with 3 subdivisions of equal length to find the approximate value of, and they give us a definite integral. The integral from 1 to 7 of x squared minus 9x plus 9 dx. So how do we do this? Well, we're going to do this the same way we did the approximate integrals in the last lesson. We are going to say, if we were to have a value of delta x, what is it going to be? Well, it's going to be b minus a over n. So in this case, we're going from 7 to 1, and we want 3 subdivisions. So each one is going to have a width of 2. So we're going to have to set up intervals that are going to go from 1 to 3, from 3 to 5, from 5 to 7, and that gets us our 3 intervals. And when we're doing our approximation, we want to use the midpoint of each one of these. So our midpoints are going to be x equals 2, x equals 4, and x equals 6. So the definite integral of from 1 to 7 of x squared minus 6x plus 9 dx is going to be approximately equal to, and actually maybe I'll use this thing, okay? It's approximately equal to the sum, as I goes from 1 to 3, of f at xi delta x. So this sum, again, is going to be, let's see, for our first interval, we're going to have f at 2, at midpoint, times the width of each interval is 2. So then for the second interval, we're using our midpoint x equals 4, so f at 4 times 2. And then for our last interval, our midpoint is 6, so f at 6, again, times 2. So we need to evaluate our function at 2, 4, and 6. So punching this into our calculator, x squared, so 1 minus 6 plus 9 is, oh wait, no, it's 2. So it's 4 minus 12 plus 9 gets us 1. All right, so that'll be 1 times 2. F at 4 is going to be 1 as well, times 2. F at 6 is going to be 9 times 2. And then we can just add these up to get 22 here as our estimate for the area. All right, so we're doing the same thing that we did in the last lesson. We're just calling it a different name as we're using sort of this different terminology here. So we're evaluating this definite integral here from 1 to 7 of our function using these approximate techniques. Now, one last point to make about areas under curves or areas above curves. Here I've taken a function f at x and I am modeling it using a left endpoint approximation, and I've drawn the rectangles there in red, as you can see. So each rectangle here, if we were to figure out, I'll do this in red, the area of each one of these rectangles is of course going to be the value of the function at some x value inside that interval times delta x. Now, in some places, so for interval 1 and 2, so a1 and a2, the value of the function is greater than 0. Okay. which means the area that we calculate is also going to be greater than 0. So that's here and here. But if we look at intervals 4 and 5, just give ourselves a bit more room here. The value of the function in those intervals is less than 0. So a negative number for f at ci multiplied by our delta x is going to give us a negative area. Okay? So in general, if our function takes on both positive and negative values on this interval where we're trying to find the area, we need to take a look at whether the value of the function is positive or negative. So if our function is greater than 0, the area in that region adds to the total. If, on the other hand, the value of the function is less than 0, the area subtracts from the total. So it's like we're adding negative area. Okay. So let's take a look at the kind of problem that you might be asked to answer here. So here's one. We actually looked at this graph at the start of the last lesson. Okay, so the graph G consists of two straight lines and a semicircle. Use it to evaluate each integral. So the integral from 0 to 2 of our function, the integral from 2 to 6 of our function, and the integral from 0 to 7 of our function. So what we want to do is divide this into three little areas here. We'll have area 1, we'll have area 2, and we'll have area 3. And we can figure out what the area of each one of these little areas actually is. So area 1 is a triangle. So if we do base times height divided by 2, the base is 2, the height is 4. So we get an area of 4 there. Area 2 is 1/2 that circle there. So it's 1/2 pi r squared. Our radius is 2. So we'll put in 2 squared. So 1/2 pi times 4 is going to be 6.28. And then area 3, that little triangle in there, is going to be 1/2. Our base is 1, our height is 1, so we just get 0.5. Okay, now the answers to all three of these integrals here are just combinations of these three areas. So if we want A, the integral from 0 to 2 of g at x dx, that means the area under the curve from x equals 0 to x equals 2. From there to there, which is just going to be a1, which is just going to be 4. For b, if we want the integral from 2 to 6 of gx, it's the entire area under the curve from 2 to 6, but this, so we want, in this case, from 2 to 6. So this is just basically a2, but because the value of g at x is less than 0 on that entire region from 2 to 6, we have to count this as a negative area. So this is going to be negative 6.28. And for c, if we want the integral from 0 to 7, okay, so this is all the way from our starting point here to our ending point here, we've got to combine all three of these areas. So area 1 is positive area, we've got to subtract area 2 because we know it's a negative area because g at x is less than 0 in that region. But then we have to add on area 3 again. So we end up with a net negative value for that integral because the net area under the curve over this interval is less than 0.